So yes, thanks for the invitation. So just I want to mention one or two things before getting on to this talk. One is this is kind of a fallback talk. I had planned to do maybe a talk on some other stuff, but I had not finished this other research, so I was not able to put up a sensible talk in time. And second, this is work that is kind of old now because I started on it back in, I think, 2019 or something. And then actually some of the ideas I had on this go back even further. And so my memory of some parts of it are a bit fuzzy. Um, anyways, so yes, so here we go. So I'm going to start with this conjecture of Ron Graham's, which was to determine with proof whether or not there are infinitely many integers n, so that 2n choose n is not divisible by 3, 5, or 7. In other words, it's co-prime to 105. And one quickly discovers that binomial coefficients are really a distractor because of the following theorem. This is due to Kummer. Kummer had many theorems due to him. So this one says that the number of times that a prime p divides n choose a is the number of carries that one does when adding a to n minus a in base p. So the real question then is, are there infinitely many integers n so that there are no carries in base 3, 5, or 7 when you add n to itself, right? Because in that case, the a, so you're looking at 2n choose n, so that it's 2n choose a, and there the a equals n. So you're adding a to itself. Another way to say that is, are there infinitely many integers n so that the base 3 digits are 0 or 1, so there are no 2's in base 3. The base 5 digits are 0, 1, or 2, and the base 7 digits are 0, 1, 2, or 3. Those are the what you're really asking for in Graham's conjecture. Okay, so Pomerantz gave a heuristic for why the answer should be yes, and the heuristic can be used to pin down for any finite set of primes whether or not there should exist infinitely many integers n such that 2n choose n is not divisible by any of the primes p1, p2 through pr, at least 3. And actually his heuristic is kind of the obvious one. So what he does is he says, let's say you pick a number n in x to 2x. There's nothing fancy special about the 2x there. We just want to say that n has size roughly x. Okay? So it will typically have about log x over log pi base pi digits. And here you're letting I range from 1 through r. And then the probability that all of those digits are less than pi over 2 is going to be the greatest integer of pi plus 1 over 2 divided by pi. That's the probability, that's the fraction of digits less than pi over 2 among all the possibilities for that digits in base pi. And then you're raising it to the number of digits. So if you make some obvious independence assumptions, so here by obvious independence assumptions, I mean, we all know that if you take a number and you write it in several different prime bases at the same time, then they're sort of uncorrelated, or the sort of what you see in base 3 seems to have nothing at all to do with what happens in base 5, and so on. Okay, so if you do that, then the probability that all of the digits have size less than pi over 2, I going from 1 through r, is the product of these probabilities. And if you work it out, that probability for the primes 3, 5, and 7, that turns out to be x to the minus 0.97. Okay, so that's if you're picking an n in x to 2x. And so, well, the fact that that's not 1 over x, it's means that you expect there to be several n's in the interval x to 2x where all the digits are small, right? Are less than pi over 2. The expected number ought to be, you take this x to the minus 0.97 and multiply it by x, and you get x to the 0.03, right? And so, if you take, since that's how many since you get at least one in the interval x to 2x, then you can take infinitely many of these dyadic intervals, and so there should be infinitely many integers n, indeed. Okay, so I now want to mention a few results from the literature, just to be scholarly here about some of these things. So the first one I want to mention is a result due to Ford and Koniagan. So they studied the p-adic valuations of central binomial coefficients in great detail. And one of the things that they showed is that for a fixed L set of n's where n to the L divides 2n choose n has positive lower density. That's maybe not too surprising because 2n choose n has many prime factors, including small prime factors. And this GCD fact is a little closer to what we're interested in, except we're considering the case n equals 105. Or I mean, the number here in the GCD, what we were considering earlier, would be 105. So they showed that if you look at the n's where the GCD of n and 2n choose n is 1, that holds for all but a small number of the n's up to x. All but at most cx over log x ends up to x. Okay, and I just want to mention this very briefly, this result of Dew and Ligarius. I think Dew was a student of Ligarius, I can't recall. So they looked at products of coefficients along a row of Pascal's triangle, and they were interested in the prime factor statistics. They were looking at like how many times does a prime p divide these products, as I recall. And here's a kind of a new one that's kind of neat. So Thomas Bloom had compiled some Erdish problems. He had this website called, in fact, the Erdish problems. And one of these was called Erdish problem number 728. And then, so let me just state the problem. So it asks about finding integers a, b, n, and k so that a plus b is n plus k, and a factorial b factorial divides n factorial k factorial, where a and b are between epsilon n and 1 minus epsilon n, and k has to have some size to it. It's at least c log n. And this student at Cambridge University named Kevin Barreto, who I believe now works for OpenAI, and maybe he also has kind of a side project with Math Incorporated, the auto formalization company. So he used GPT 5.2 Pro, and then also Harmonic's Aristotle, which does auto formalization, and completely solved the problem. That problem of Erdos. And he proved there are infinitely many solutions, A, B, and N, with K between C1 log N and C2 log N, which is in spirit what Erdos, that's the kind of, that was what Erdos was asking for. And this doesn't seem to have anything to do with binomial coefficients, but then you think about it for a second and you realize a factorial b factorial is the denominator of a binomial coefficient, as is n factorial k factorial. So you can transform this into a question about binomial coefficients, actually one binomial coefficient dividing another. The success of this and also some of the other Erdos problems using GPT 5.2 Pro, the expensive model that you have to pay $200 a month for, would make one think maybe some more problems related to binomial coefficients might fall out of that approach. And then I wanted to also mention just two results about digits and several bases. So there's a paper of Burrell and Yu, who studied integers whose expansions in different bases use only very few digits, very, very small digits. For example, digits 0 and 1 in bases 3, 5, and 7, and they prove finiteness results in some natural settings and obtain quantitative bounds on how often restricted digit phenomena can occur. And so in parallel, there's a substantial literature on primes with restricted digits. For example, Maynard shows that there are infinitely many primes whose base Q expansion emits a fixed digit. That would be like if you expanded n in base 10, say, and you want primes that don't have 1 as any of the digits, for example. And then Bourgain and others allows one to prescribe a positive proportion of the digits of a prime. You have to be careful, of course, to avoid, like, if the least significant digit is 2, for example, then the number is obviously even and can't be prime. But, you get rid of sort of the obvious restrictions, then, it's a non-trivial result, highly non-trivial result, in fact. So these problems use many of the same Fourier analytic ideas that show up in Graham's problem. Okay. So I and my collaborators, so I have 2 sets of collaborators. One was a paper by Ahmed Mousavi, who was a PhD student of mine, and then also Maxie Schmidt, who was also a PhD student of mine for a little while. Then she moved to another advisor, and anyways, so we had that paper, and then there was another paper with Thomas Bloom that came later that improved our result. So I'll talk about both of these results. We worked on this problem for a long time, Graham's original problem, and we weren't able to solve it. We decided to try to still produce a nice result to see what we could get out of our methods. And so we can think of it as like 2 constraints about how to write a paper. So the first constraint is find some nice problem that is fairly non-trivial to solve, where, although it doesn't imply Graham's conjecture, is more general in that it works for several primes at once. Okay, that's constraint number 1. And then another constraint is the statement of the theorem has to be relatively simple. It can't be like a long chain of nested quantifiers, like for every x there exists a y and a z, such that for every w there exists alpha, beta, and gamma, and so on. We don't want a result like that. We want something like maybe with 1 quantifier, if possible. Okay, so in work with, so mostly what I'm going to talk about now is this original work with Hamid and Maxie, and then I will, at the end, maybe talk about throughout, I'll mention also how the work with Thomas Bloom differs. Okay, so here is our original, and work with Hamid and Maxie. Our original theorem looked like the following. So we had that for every r, at least 1, and epsilon positive, and r sufficiently large primes, p1 through pr, greater than p naught of r and epsilon, there are infinitely many integers n, so that all but epsilon fraction of the base pi digits of n are less than pi over 2 for I going from 1 through r. Okay, so before I press on with an example of this, I want to point out 1 or 2 things about this theorem. So actually, maybe I will do this example first, and then I'll come back to what I was going to say. Okay. For example, if you take a number like the following in base 7, so if it's in base 7, it has the possible digits are 0 through 6. Okay. And you look at this number and you see that it has a digit that's 5, it has another digit that's 4, and it has a digit that's 6. Okay. So these 3 numbers are greater than 7 over 2, which is 3.5, right? So those would be bad digits, but it doesn't have too many of them. It only has 3 of them, So this would be the kind of number that we're trying to count. We're trying to find that there are infinitely many numbers kind of like that, depending on what choice of epsilon you make. Okay, but not just in base 7, we would want to have a result like this that works in several bases at the same time. So one weakness of this theorem I want to point out, and this really caused a lot of consternation trying to improve this is that when you fix the epsilon in the beginning, the primes, you see, have to be greater than some function of epsilon. So the smaller you take epsilon, the larger you have to take the primes to be to get a result like this by this original theorem. Okay, and I mentioned that here at the bottom. And then in subsequent work with Thomas Bloom, Thomas found a way to remove this dependency. And it's a technical improvement to our approach. Maybe I'll describe it a little bit when I get to the end of the talk. And the result itself, so here is the result. We have that for every r at least 2 and bases g1 through gr at least 2, such that gi to the ai is not gj to the bj for I not equal to j, and integers ai and bj at least 1 with associated, and we have associated, this shouldn't be integers, these should be fractions. Maybe I should just get a, whoops, those are not integers. Okay, there we go. Such that, and there's this condition here, a technical condition, the sum j going from 1 through r log base gj of 320r to the fifth over kappa j has to be less than 1 over 2r. If that happens, then for any epsilon, there are infinitely many integers in, such that for all the j between 1 and r, all but at most epsilon fraction of the base gj digits of n, actually, technically the number of those digits would be would be log n over log gj. So this is not epsilon fraction of those digits, it's epsilon over log, or epsilon times log gj fraction. But the epsilon you can take smaller and smaller, so that's not a problem. Of n are less than kappa j gj. Okay, so let me point out a few things here. So first of all, this technical condition at the beginning is nothing really. If we want gi to the ai not being gj to the bj, all that's about is, like, if you write a number in base 2 and then you also write a number in base 4, the digits are correlated, right? Obviously, if you know, they're sort of locally correlated. If you know 2 digits, if you know a single digit in base 4, that corresponds to 2 of the base 2 digits, right? So there's nothing really to that. And obviously, if the GIs are prime, then this condition you don't have to worry about this condition at all. It only would come up if, in the case when the GIs are composite. Okay, and then this second thing to note, really the main thing I want to point out, is the fact that here we're picking the bases first before we pick the epsilon, right? So the order of the quantifiers is working in our favor for this problem. So, once you've chosen these bases, as long as it satisfies this technical condition, which has nothing to do with epsilon, then you can take epsilon as small as you like, and you get the infinitely many n's. Okay. And another thing to point out is that we don't have, we're not getting the digits to be less than pi over 2 here, but we have a more general result. We're allowing these ki's can be, they don't have to be like a half, they could be like a fourth or a tenth, whatever you want to take them to be, as long as they fit in 0 to 1. Okay, that's another thing. And then it's worth pointing out that this technical condition is really nothing, because you may worry, do you even get any at all given this technical condition? The reason that you do is that, well, if you write out this log gj of this number, this would equal, log of this number, log base e of this number divided by log base e of gj, right? And if you take the gj is big enough, then you can get this to be as small as you like. So in particular, you can get it to be less than 1 over 2r. So it's not a problem. You can definitely get this condition to be satisfied as long as you take the basis to be large enough. Okay. So that's the theorem, which fixes several issues in the previous theorem that I had stated. Okay, so now I want to describe a technique and actually I discovered it myself, and then I was a bit miffed to find that Erdős, Graham, and Ruja Strauss had already beaten me to it by decades. This was, I guess, back in grad school, I had discovered this, and then independently, and then discovered later that they had come up with it themselves. So they showed that for any pair of primes p and q at least 3, there are infinitely many integers n such that all of the base p digits are less than p over 2 and the base q digits are less than q over 2. So not epsilon, all but epsilon fraction, but all of them, right? And so our approach will follow a similar line of reasoning, but with some major differences I'll describe below. Okay, so let me give you the idea of how they do it. So the idea, let's do their technique in the case of 2 bases. We'll do base 3 and also base 5. And so what you do is you can start like in base 3 and pick a 1, which would correspond to 1 and a bunch of zeros, which would correspond to a power of 3. And you take that number and you write it in base 5, and it turns out you get this thing on the right-hand side. Maybe it's helpful to have some to shade it in. Yeah, and get this number on the right-hand side, right? Okay, and then, but now you notice that there's this 4. This 4 is bad because it's bigger than 5 halves, you know. So we want to get rid of that 4. So what could we do? Well, we could add a lower power of 3. We could add an extra 1 here, which still avoids having any carries in base 3. And if I do that, if I put the 1 there, what it will do to that 4 is it'll add a 1 to it, and you'll get a 4 plus 1 is 5, which is 0 carry a 1, and then 1 plus 1 gives you a 2, which is okay. Having a 2 there is okay. 2 is still fine as far as those digits less than p over 2 go, or q over 2. Okay, so but now the next problematic digit would be this 3. We need to get rid of the 3. Okay, so we can add an even lower power of power of 3 here, and that will result in a 2 in that position. And 3 plus 2 is 5 is 0 carry a 1. Now you get a 2. And notice it doesn't mess at all with these upper digits, right? Obviously, that's going to be true, because if you add lower and lower powers of 3, it won't have any effect on these higher digits that we had corrected earlier. Okay, and so now the next bad digit is this 4, and you can add another power of 3, and you can clear away the 4, and so on and so on and so on, and you can get all the way down to getting just 0s and 1s in base 3 and 0s, 1s, and 2s in base 5. Okay, that's how the idea works. How the Erdős, Graham, Ruja, Strauss approach works. Okay, but now if you try to do this for using 3 or more primes at once, you run into 2 problems. One is that you can get yourself into a situation where no single digit change will fix up all the digits of the number when expressed in the other bases. Like, you know, you can definitely get, as we saw, you can get 2 bases to work fine. But if you try to get the third, you can get yourself to where, in a situation where you can correct for digits in one of the bases, but then it messes up the digits in the other base. Okay, so that's problematic.
A quick question for
Yes.
2 bases. So this argument will construct infinitely many n with the desired property.
Yes. Yes.
So is there a quantitative result known that there is polynomially many integers in an interval of length n, where there's no carry in base 3 and base 5?
Well, it would be exponential in, let's see, the exponential. Yeah, I guess it would be whatever the right. So it'd be like, yeah, you're right. It would be a power of. Yes, you can do that. Certainly, you can see. I mean, I don't think they did it in their paper, but I'm sure you could do it. Yes, I don't think you could get the optimal bound, whatever the optimal bound is. You know, whatever the heuristic gives. I don't think you could get that by this method, but I can definitely believe you can get a pretty strong bound. Yes, for sure. Okay, so so that was the, hold on a second, I got a call right now. Hello? I'm in the middle of a talk right now at Georgia Tech. What is it again? Are you asking? Okay. Okay, thanks. Bye. Yeah, so that was pest control calling me. Anyways, so and then the second problem is that there can be non-trivial dependencies in the digits in different bases that make applying certain standard equidistribution approaches not work as hoped. This is a little bit kind of so before, when I was talking about how, if you write a number in one base and you look at a certain block of digits, then the digits in the other base can be completely uncorrelated, right? And if you just do two bases, and you would expect the same thing to happen if you did three bases and four bases and five bases. In general, you can't expect that something like that happens. And because you can't expect something like that happens, that's going to complicate things tremendously. But we can still fix it. Okay, so the idea basically is that what I want to do is, instead of trying to make single digit changes, I want to make blocks of digit changes. That's really the idea behind how to fix up this, how to make it work for many bases at once. Okay, and I just want to begin maybe by trying to explain this in the case of two bases. Okay, we already know how to do two bases when you make single digit errors, so you may wonder, so what is the point? Well, this is basically just to show you the idea of how this method works. Okay, so the point is I want to make changes to blocks of digits in two bases, and then we'll talk about how to do three bases and four bases and so on. Okay, so we suppose we have some initial number n naught that we have constructed, and let's say when we write it in base p1, it can be expressed as n naught is m times p1 to the l plus k. So what am I thinking of here? I'm imagining that I have run some algorithm a couple steps, and the m here is like those upper digits in base p1 that I have created so far. And then what I want to do is, instead of adding one more digit in this base that's a little lower down, I want to add a whole block of digits that is a little lower down. Okay, so I want to add to that, I want to create another number, n1, which is m p1 to the l plus k plus n p1 to the l, where n is between 0 and p1 to the k minus 1. Okay, so what are the leading digits that are affected by this new term, n p1 to the l in base p2, in the base p2 expansion of n1? Okay, so to answer this, we can begin by just writing p1 to the l. The p1 to the l is the same as that p1 to the l. We write it in its base p2 expansion, and so let's say it has some digits like that: c l prime p2 to the l prime, c l prime minus 1 p2 to the l prime minus 1, and so on. And then I have that L prime turns out to be the greatest integer of L log P1 over log P2. Okay, so now we can translate everything to the interval 0, 1 by dividing by P2 to the L prime plus 1. So in other words, I take this P1 to the L and I divide it by P2 to the L prime plus 1, and I get this here. I get CL prime over P2, etc. Okay, so let's call that number alpha sub L. And so we could alternatively write it as P1 to the gamma, and the gamma you can solve here. It's given by that. And so I have that if you work out what, you could also write this as just a power of P2. This alpha L could also be written as P2 to the fractional part of L log P1 over log P2 minus 1. Okay, and so the problem basically that we want to be able to solve in order to make our adding the blocks of digits to clean up the digits in base P2 is we want to try to say that for any real number beta, and we can find an n between 0 and P1 to the k minus 1 with all small digits base P1 such that in alpha L plus beta has leading digits small in base P2. Okay, that would be the ideal situation that we could be in. Okay, where's the beta coming from? So the beta is those digits of n naught when we write them in base P2. Okay, so remember the n naught was what we started with back here, and that was, we wrote that in base P1, but we can also write it in base P2, and it's got some bad digits in base P2, right? That's what the beta is going to be, basically. Right, and so we want to fix up, so we want to fix those up. Those digits have been normalized by dividing by P2 to the L prime plus 1, and to put in 0, 1. So that P2 to the L prime plus the beta actually, so if I write n naught over P2 to the L prime plus 1, that will actually be a number bigger than 1, but ultimately we'll take a fractional part anyway. Okay. So actually, what we're looking at is, if you look at the fractional part of n alpha L plus beta, it equals this, which is our n1 divided by P2 to the L prime plus 1, that fractional part of that. Okay, and so as I say here, so now the way that I've written this, I've actually done a sleight of hand and ignored some potential what I call base P2 pollution coming from the factor n. This n, when I multiply this n, you see up here when I had the P1 to the L, and I wrote it here in base P2 after I divided by this power of P2, I didn't have, that was a number in 0, 1. But then if I multiply that by n, then it isn't all of a sudden, and I can get a few extra bad digits in base P2 when I, if I remove the fractional part. Okay, so that's what this is talking about here, but you can throw that into an error term ultimately. It's not too big of a problem. Okay, so anyways, that's the kind of thing that we would like to be able to do, is we'd like to be able to say that for that for any real number beta, so if we're giving this alpha sub L, that for any real number beta, we can find an n with small digits in base P1, so that n alpha L plus beta has leading digits that are small in base P2. Okay, and again, all the digits of this fractional part will be, that number is less than 1. Okay. Okay, so after the dust has settled, what exactly is the problem that we should be solving here for this quote, more robust approach that we can generalize? The problem is that we let k be some slow-growing function tending to infinity with n, and we want to show that for every epsilon and n sufficiently large in terms of epsilon, the following holds for all but at most epsilon in integers L less than or equal to n. And it's that for an arbitrary beta, there exists an n up to a small n such that the fractional part of this is in some set S, where you have this set S is contained in 0, 1, and its digits in base P2 are small. They go only up to P2 over 2. So the thing to notice here is that you have here, you're fixing up k digits in base P2, and what potential price are you paying by this? Remember, I said before you had this pollution that you get from this little n. Well, you're only losing, it only has epsilon k digits. So you have epsilon k digits here. It allows you to fix up k digits here. So you're not losing too much as a result of that. Okay. So now what happens when you try to generalize this for 3 primes and 4 primes and so on? Okay, so then you can do that, and we can define this parameter alpha sub L prime, which is P3 to the L log P1 over log P3 fractional part minus 1. And then the problem becomes this. So you want to show that for all but at most epsilon n integers L up to n, for arbitrary beta and beta prime in R, there exists n up to P1 to the epsilon k such that you take this pair of fractional parts in alpha L plus beta and alpha L prime plus beta prime, that it's in a set S cross S prime. You saw S before. S prime is the analog of that for base P3. So it's numbers mod 1 that have the leading k digits are less than P3 over 2. Okay, and now if we had that, the fractional part of L log P1 over log P2 and the fractional part of L log P1 over log P3, if we had that was equidistributed mod 1 as we vary over L, then that would mean that if you look at the alpha L prime here, which is P3 to a power, right? This here is the same as like this down here. Then, if this can be any number in 0, 1 at the same time that this can be any number in 0, 1, then you can sort of get the alpha L and alpha L primes to be uncorrelated. And because you can get them to be uncorrelated, you can get both of these. It's not too difficult to prove using some Fourier analysis that you can get this to be in S cross S prime. Okay, and that would be what you need to solve this intermediate proposition to solve the original problem. Okay, so what happens if you try to, so that's your hope, is that these would be, these are, that they're, if you had that these were equidistributed mod 1, then you'd be good. Okay, so, well, there's a theorem called Weil's equidistribution theorem, Weil's equidistribution theorem in 2 dimensions, and it holds if and only if the numbers 1 log P1 over log P2 and log P1 over log P3 are linearly independent over the rationals, which is saying that 1 over log P1, 1 over log P2, 1 over log P3 are linearly independent over the rationals. Unfortunately, this isn't known to hold, and it's not a trivial consequence of, for example, the fundamental theorem of arithmetic or Baker's linear forms and logarithms or any other elementary, Baker's linear forms and logarithms is not elementary, but any simple trick that you might try will not allow you to do that. There is a conjecture called Shandiel's conjecture that you could use to do it, but again, that's only a conditional. That would only be a conditional result. Okay, so well, there is a way around this. The way around it is that you don't actually need these to be these vectors to be equidistributed mod 1. They can be correlated, and that's still okay. And let me just make sure I'm not skipping over some stuff here. Yeah, okay. So yeah, I say that here. So there are thus 2 options here. We can either try to prove the independence result, which, as I said, is hopelessly difficult. There's no way to do that, or assume potential dependencies exist and somehow work with those. And so we switch to option 2, as I said. So I gave an example here of what that boils down to. So we can consider a very simple kind of linear dependence. We could say, let's say we had log P1 over log P2 minus log P1 over log P3 was an integer. And then we would have that like the fractional part of L log P1 over log P2 is the same as the fractional part of L log P1 over log P3. And then that would mean that this pair of numbers that you get, alpha L and alpha L prime, have to lie on a curve of the following shape. P2 to the T minus 1, P3 to the T minus 1, where T is the fractional part of L log P1 over log P2. That ratio is not a rational number from the fundamental theorem of arithmetic, and so this T will range over 0, 1. And so you basically have the curve of all points like that where T ranges over 0, 1, which is what I say here, basically. And so then to solve the problem, in this case, we need to show that for density 1 of the points, T in 0, 1, there's an n up to P1 to the epsilon k, so that n times this vector plus beta beta prime is congruent to some SS prime mod 1, like that. And then that can be solved using Fourier analysis, and we chose to use discrete Fourier analysis to do it. Okay, so yeah, you can do that. You can show that for most of the t's, not that we get it for all of the t's, but density 1 of the t's, we can get that to be true. Let me now mention some of the bottleneck, or some of the pain that went into trying to get this to work. Okay, so I initially tried to prove this using Fourier analysis methods, and I sort of lumped all the choices of t and the choices of n and all the and then for arbitrary beta beta prime into one giant Fourier analysis problem and calculation, and it didn't work. I couldn't get it to work, and despite spending a lot of time on it. And the problem is that the curve that you get with this P2 to the T minus 1, P3 to the T minus 1, or what the more general version is, depending on what kind of linear relation you get here. As I said, this was only one example of a linear relation, but there are many other potential integer linear relations you might get. So what the problem is that curve that you get, not just when you have 3 primes, but when you have 4, 5, 6, any number of bases at the same time, is that this curve could be like flat in places. It can be very flat in places. And this flatness kind of screws up the Fourier analysis in a really nasty way. And so then I struggled. So then I thought, well, let's just try to eliminate that. And can we just show that the flatness doesn't happen very often? And then that turned out to be related to, I thought it would be a sort of a trivial exercise with geometric ideas, some just really simple geometry, but I couldn't do it. And it turned out that what I needed was some facts about generalized Vandermonde matrices. And so I had to go look up this paper in a Russian text translated to English that gave me what I needed, but then the paper was really very technical. And so I kind of gave up on that, and I decided to try to find a simpler way to do it. And I did. And I should also point out that there was this generalized Vandermonde matrices. I also tried to use Schur functions to try to produce what I needed. And that just seemed too difficult because the Schur functions didn't quite give me what I wanted. And so ultimately, I was able to take the proof that was in this Russian textbook, and I just extracted kind of the key parts of it that I needed, and then I boiled down to some technical lemma that was fairly simple. It had a fairly elementary and short proof. So that was good. I was very happy that all worked out. And then there was still this problem of this, the fact that initially you pick the epsilon and then you pick the primes. And I wanted to make it so that you pick the primes first and then you pick the epsilon. And then Thomas had this really nice way of using, and I actually didn't think you could improve this method at all. I didn't think it was possible to do it. And then Thomas came up with this really nice technical proposition, lemma, whatever you want to call it, about involving Fourier analysis on numbers in different bases at the same time, or even just one base, and where you want to bound from above the number of large Fourier coefficients, the large Fourier spectrum. And that turned out to be really a key ingredient that we needed. And there's some other very highly non-trivial technical additions to the paper as well, that to go even further, like, well, I'm not going to get into it. But anyways, yeah, that, to make a long story short, it wasn't as simple as I'm making it look here. There's a lot of details that go into this proof. Okay, I just want to maybe wrap up with some open questions. I'm really glad that this turned out to fit into 50 minutes. I was afraid it would either be too short or too long. I think I did it, cut things the right way here. So one is, can one give reasonably good counts on the number of n up to n such that 2n choose n is divisible by pi to multiplicity little o log n for I goes from 1 through r. So this is basically another way of stating our result. But here we're asking about finding good counts on how many n's there are, right? This is basically Cosman's question when he asked it about two primes bases at the same time. Well, here we're basically asking the same question about several bases at the same time, and where this multiplicity of little o log n, that's where you're basically saying that all but little o log n of the digits are small when you write it in different bases at the same time. And then another one is, how close to the limits of Pomerantz's heuristic can we get? So what that's about is, if you go back to the theorem that I had here, this theorem with Thomas, where is it? We have this condition, you see, on the log. We have this technical condition here, which is, so you need, if you pick like the kj's to be a half, and you want to, you would need your prime, if you're working with prime bases, you need the primes big enough so that this inequality holds. Well, there's no reason to believe that, this is optimal, right? The 320 r to the fifth, who knows? It could be, maybe you can, this is obviously going to be far away from Pomerantz's heuristic. So the question is, how close to his original heuristic can you get? And then another question is, so what other kinds of problems can one attack that involves expanding numbers into multiple different bases at the same time? So we've seen our theorem, and I mentioned also Maynard's result and Bourgain's result. There are some results in the literature and along these lines, and it's good to see what kinds of problems like that one can solve. And then really the one that I'm really kind of least hopeful about, but would be really great, would be, we can't solve Shannul's conjecture probably, but we can at least try to say something non-trivial about linear dependencies of numbers 1 over log p1 to 1 over log pr. What can we say? So is it possible to derive some information here that would help us improve the results in the paper? You could even just do this for like 3 primes, like, is 1 over log p1, or no, is 1 over log p1, 1 over log p2, 1 over log p3, for example. Can you get linear dependencies in that to equal 0, for example, linear combinations of those to be 0? Okay. Anyways, I'll leave it there, I guess.
Thank you, Ernie. Let's thank Ernie
Yes.
for the nice talk. Before questions.